Well, hello friends. Today we're going to go on a little code tour again, since it's been a while, and it's going to be about the kernel virtual memory system. So I have made a little bit of help material here for myself. So we're going to go through like how virtual memory works, how stuff is allocated, how physical memory is managed, stuff like that. But here is a very high level concept picture of all the big concepts in the Serenity kernel. And we'll be going into some other things as well, but on the highest level, we have processes that are running in the kernel, and each process has a set of regions, and those regions, each region points to some kind of VM object. And there are three kinds of VM object. We can all see them all here. There are inode VM objects that point to some inode in the file system. There are purgable VM objects, which are a special kind of memory that we talked about recently that the kernel can take away from the process whenever the kernel wants. And then we have anonymous VM objects, which are by far the most common. And these are just like when you call mmap with the usual parameters, then you get one of these. It's not backed by a file, it's backed by RAM, and the kernel is not going to take it from you. And as you can see here also, we have a region in two separate processes, and they're both pointing to the same VM object, same anonymous VM object, so it's shared between those processes. They actually have the same memory inside of them, both of them. And then over here we also have an anonymous VM object that's private, which just means that this is only accessed by this process. And I wanted to illustrate also that there are more inodes in the system. Not all inodes have a corresponding inode VM object. You only get one of these objects if you actually mmap the inode. So this is the very, very high level overview, but let's look a bit more at the, or actually no, let me show you a few more slides here. Then it's important also to know that regions always point to a VM object, like I was saying. And then a VM object internally is built up of a list of physical pages. And each physical page is 4 kilobytes of actual RAM. And the regions, they don't know which physical pages they are referring to. They only know which VM object they refer to and what slice of the VM object they refer to. So this region here and this region here, they point to the same VM object, but they refer to different parts of it. And that's perfectly possible. You can mmap the same piece of shared memory, for example, and you mmap at two different offsets with two different sizes, and you end up with this type of thing. But the important thing to know here is that if somebody were to expand their mapping so that they would look like this instead, then they would be sharing this memory over here. As it is right now, although the VM object is shared between the regions, they don't actually share any memory. And a bit of a sad thing is that we have, or I wouldn't say sad, but we currently don't understand that this piece of memory here and this here is wasted. But this is a situation that can come up sometimes. I don't know why I chose this particular situation. It's maybe not the most common, but the important thing is to understand regions all point to VM objects. They can be shared. They can also be private. They could be only a single region, like this scenario is very typical. Although then it would be more like this. This is by far the most common scenario, where a region has its own private VM object and it refers to the whole VM object. Anyway, another important thing to know about is that these physical pages down here, they are on demand loaded. So say that we had the setup that we did have up here. It would probably look like this in reality, because we only allocate physical pages when we need to. So it's very lazy. And this happens through the page fault mechanism, which we'll be seeing soon enough. And anyways, so that's what's important to know about this. And I guess we can look at the last one as well. Every process has a bunch of regions, as we saw here. Each process has regions, and it's important to know that regions are referred to virtual memory, so they have virtual addresses. They have a virtual address range, which is called a range. Each region is at some address in the process address space. It has some size. And these ranges, they are given out and managed by this thing called a range allocator. That's how the process knows that if you call mmap twice, it doesn't give you the same address twice. So range allocator keeps track of which parts of the address space are available. And if you deallocate a region, then that range is put back into the range allocator, which merges it with the available ranges and so on. And the object that holds onto the range allocator is actually this thing called a page directory, which is an abstraction of the CPU page directory. So each process has a page directory, and then the page directory has a range allocator. And the reason that it's set up that way is that it's mostly because it maps nicely to the CPU, and then it makes implementing exec a little bit easier, because before we know if we're going to succeed or not, we can create a temporary page directory, load a new executable into that page directory, and then when we see, okay, this exec is going to work out, then we can replace our existing page directory with a new one. But if during the execution of exec, we discover that this is not going to work out, then we can just get rid of the page directory that we've been constructing. And it just simplifies exec, basically. But yeah, so this has been the visual introduction, I guess. Let's go to the code. We'll probably get back to the little graphics there. But let's start at boot. So the first time when we enter the kernel in C++, or actually maybe we should even look at a little deeper than that. We should look at boot.s. So the bootloader will call this code. It's just some assembly setup code that we have. And the important thing to know is that in the multi-boot header, we specify that we want memory info. So we say here, our multi-boot flags, which are instantiated here, we specify memory info. This means that the bootloader will give us a table which has all of the available memory regions in it in RAM. And it's just a list of the available memory that you can iterate. So, oh shit, I forgot one more thing. And also, in the bootloader, we have, right here, we reserve some space for our initial kernel page tables. We reserve three pages of 4 kilobytes each. This is just so that we have somewhere that we can put the initial page tables that the bootloader is aware of, because the bootloader then the bootloader looks at all of this in the boot part here, and it's able to it knows that it's not going to put anything on there, so they don't trample on each other, basically. Anyway, so we enter the C++ kernel in init, and we do a little bit of setup, CPU setup, and then we initialize kmalloc. Kmalloc, we're not going to go into kmalloc too much in this video, but basically it's a very simple first fit allocator that allocates out of a fixed size. It's a 3 megabyte pool of 8 byte chunks, and that's what we use for small allocations in the kernel. Although we also have a slab allocator, which is if you have specifically for these sizes. So if you want an 8 byte, 16 byte, 32 byte, or 48 byte allocation, you can use the slab allocator instead, which operates using a free list. And so it's a lot faster, and it's a lot more efficient because there's no waste, since you know that you are getting exactly as much space as you asked for. So we have those two allocators in the kernel. Most code uses kmalloc. I should try to get more stuff to use slab allocation, but I haven't spent too much time on it. Okay. So after that comes a bunch of stuff that we're not going to look at today, setting up various things. But the important stuff, let's see, where is it? Right down here, right after we say starting the Serenity operating system. we call memory manager initialize. Now this is where all the fun stuff is for today. And by the way, this physical address for the kernel page tables, that's the address of the reserved space that I mentioned in the boot.s. So, oh, I guess we just instantiate one here. So then we should go to the constructor. So here we create the first kernel page directory. I'll maximize this. And we call create at fixed address. So that's the reserved address that we were setting up. So the first one is a page directory, and then the second two reserved addresses are, or reserved pages are page table 0 and page table 1, respectively. And then we call initialize paging. And this is where most of the setup is going to happen. So first thing we do is just zero out page table 1 and page table 0. And then we want to make sure that if you try to access a null pointer, then we won't crash. So without that, things can get very, very strange very fast. So we make sure that we map the first page with protection. So this just basically inserts some values into the kernel page table corresponding to the very first part of memory. I mean, the very first part of the virtual address space. So addresses 0 through 4 kilobytes. That's the first page. And we just say not present, basically. This is the important part. And then the rest is less important, but not present. This makes sure that if you try to access that memory, you will get a page fault. You always get a page fault if you access memory that's not present. And then also it's important here to know that flush TLB, you always have to flush the translation look-aside buffer whenever you are changing the rules for some virtual address. Then this basically tells the CPU, hey, if you cached anything about the address that I have been updating here, so address 0 through 4K, if you cached anything about it, you got to throw away that cache right now. And we make sure that we do that, so that, because otherwise if you were accessing a null pointer directly after, it might still be cached, that's okay. So that's why we get rid of that cache. And oh, I guess I should mention, we always try to do very specific TLB flushes. So we try to flush only one page at a time. It is possible to flush the entire TLB, but that is very inefficient because then the kernel has to recreate the TLB as it goes again. So whenever possible, we try to flush only the parts of the TLB that actually changed. But of course, whenever you're switching between processes, we end up effectively flushing most of the TLB anyway. Because we changed page tables. Anyways, so where were we? Map protected, right. And then what we do, so this is something that is not going to stay this way, but let's just talk about how it works now because that's relevant. So we identity map the bottom 8 megabytes of the virtual address space. And what that means is the virtual addresses between 0 and 8 megabytes, or actually between 4 kilobytes and 8 megabytes, because the first 4 kilobytes, they are the null pointer page, so we don't map those, but from 4 kilobytes up to 8 megabytes, we identity map, which means that the virtual address and the physical address are identical. So it's important to know the difference between physical memory and virtual memory. So every process in Serenity has its own virtual address space, but the virtual addresses are not the same as the physical addresses. The physical addresses are the literal addresses of the RAM bytes. And that's what you would use if you were in a DOS environment, for instance. You're working with the physical addresses directly. But in protected mode, then you always have virtual addresses that the CPU then has all these rules and tables for mapping into the actual physical addresses. But I mean, that's pretty basic stuff, but it's important to know about it. So the bottom 8 megabytes, and here's a little ad hoc map of the bottom 8 megabytes, what's going on there. So the first megabyte, we just leave it alone. That's it has some stuff like the VGA text buffer mapped into it and stuff. So we're just not touching that right now. And then between 1 and 3 megabytes, we have the kernel image loaded. And then we have a single special page just before 2 megabyte mark, which is a quick map page. And quick map is just a hack in the kernel. If you want to quickly map a page, a physical page of memory at a known address, known virtual address, then you can do that. But you can only have one quick mapped page at a time. So this just bypasses all of the regular page table allocation mechanisms and just says, hey, map this thing for me right now. I'm just going to copy something into it or out of it and then unmap it right away. So it's a hack for that. And here we have 2 megabytes of the kmalloc eternal allocator between 2 and 4. This allocator is an allocator where there's no free. So the allocations you make, they are eternal. It's used by various things in the kernel, just things that we know we're never going to delete, basically. It's just a convenient way to heap allocate and not, you don't have to store any metadata about these allocations because you don't need to free them. And then we have 3 megabytes of regular kmalloc. Oh, and I should mention the slab allocator actually allocates its storage space using kmalloc eternal. So that's what most of this is. It's slab allocator storage, actually. So kmalloc space is 3 megabytes, and then the last megabyte before the 8 megabyte mark is what we call supervisor physical pages. And these are just 1 megabyte of physical pages that are reserved for the supervisor, which is the kernel or whatever. And in practice, those are all used for page tables. So whenever we want to allocate a page table, we get a supervisor physical page. So it's just a way to have a bunch of pages that are reserved for the kernel, basically. We could use user space physical pages for that too. We could like mash them all together and stop reserving pages, but it seemed to me like it was a reasonable thing to reserve some pages for the kernel so that whenever it needs to create a page table, it doesn't have to worry that user space has stolen all the pages. This is probably not a great design, actually, but we'll see. Anyways, and then after 8 megabytes, it's all the user space physical pages. So everything above the 8 megabyte mark in the physical memory is available to user space. And you can allocate it. And then when it comes to virtual memory, between 0 and 8, that's all identity mapped, although maybe this should say like 4 KB to that, and then 0 to 4 KB. Null page, because that's so null dereferences crash. And then this is identity mapped, and then in between here, so 8 meg through what is it, 768 meg. Suddenly we are fixing this up a little bit here, but it's probably a good thing. Wait, 768, that doesn't make any sense. 3 gig. User available to user space. Right, so all of the user space addresses are going to end up in this range. And then 3 gig to 4 gig is kernel-only virtual address space. Anything above this address is kernel. So that's the map. And then I mentioned that we get these memory maps from the bootloader, right? And here we actually iterate over those maps or tables. And what we are doing here is we are mashing together and figuring out what are the contiguous regions of physical memory And because we just get a list of regions, maybe we can see what one looks like actually if we just start up, but don't let it go for too long. Yeah, we print them out here. So we get these, we get a base address and a length. And you can see that, for instance, this one starts at 0 and ends here, and then this next region starts here, right where this one left off, but it's of a different type. So I think this one is that it's reserved for some reason or something like that. So you're supposed to know that you can't use this memory, and I think 1 is the one that's available. So technically we could probably use from 0 up to this address, but we don't. And then likewise, here is the largest piece of memory. It's between 1 megabyte and however much this is, whatever the max of my emulator settings at the moment. And this algorithm here, it just walks over this table and mashes together all of the regions with type 1, all of these parts with type 1, and figures out how big they are. And then what we do is we create physical region objects. And a physical region is basically it's a lower and an upper part, or it's not a lower and upper part. It's an offset in size into physical memory, and then you can allocate pages out of this because it has a bitmap, so it keeps track of which pages in this physical region of pages have we given out to the kernel and which ones are still available. And there are probably better data structures for this, but this is one that we're using at the moment, and it's working out fine so far. So basically, the API of physical region is, the important part is take free page, which will give you a page, and return page. Then there are some different ways of doing that, but essentially you take a page from it and then you give a page back to it, and it updates the bitmap accordingly. And sometimes you end up with many physical regions because the bootloader tells you that, like, here's some memory, here's some other memory, and you got to allocate out of all of them. So that's what this guy is for. And we store these in the memory manager object, in these vectors here of physical regions. So we have one for user space and one for supervisor. It's just to make sure that that thing that I mentioned, that we keep the kernel only physical pages separate so that the user space can't steal them. So let's get back to that. So after here, we have, and here we just count how many of those we found, how many super ones we found, how many user ones we found. And after that, we are basically done. We're ready to rock. So here we turn on this thing called, what is it? It's some global bit in page tables, and the global bit, it means that you can say that a page table entry is, it should not be, it doesn't need to be flushed from the TLB when you are, if you're switching between two page directories, then any page directory entry or page table entry that has the global bit set can be kept in the TLB cache. And for instance, this is useful in Serenity because every process has the kernel mapped in the all those bottom 8 megabyte things and everything above the 3 gigabyte mark. All of those page mappings, they are the same no matter which process you're running. So we set the global bit for those, and then that means that the CPU doesn't throw away the TLB caches when switching between different processes for those addresses. It only throws away everything in between, everything that's user space specific. So that's what that bit is about. And then we have this code here is just sets the CR3 register of the x86 CPU. That's the address of the current page directory, and that's something that we have to switch between when we are switching processes. So here we just set it to point to the kernel page directory, and the kernel page directory is, you can always switch to it if you want, then it doesn't have any user space addresses mapped. It only has all of the kernel addresses mapped. And then after we've assigned CR3, we turn on the paging bit in the CR0 register, and paging is now up. Now we are, paging means that the CPU operates on virtual addresses now instead of physical ones. So right after here, we are now running in virtual addresses, which is pretty cool. So that's how that is set up. Now, if we go back to init, let's see. So after this point, it's now possible to, kmalloc and stuff was already set up. But now, what this enables now is page allocation. So you are able to create VM objects that allocate physical pages. And there's nothing really specific to that happening here, but the interesting stuff starts to happen once we create some processes. So down here we create a first process called init stage 2, which is just the continuation of the initialization code. And creating a process, let's go look at that. Process cpp, create kernel process. So what we do here is we make a new process. Can we go to the process constructor? So when we make a new process, the very first thing that we do here is we create a page directory. So we make one for user space, we say. And here comes this important part, by the way. If we are forking, then we want to make sure that we have the same virtual address mappings and stuff as the process that we are forking from. So when we create the page directory for a process, we have to pass it the range allocator of the fork parent if we have a fork parent. In the kernel, when you're just spawning a new process, you don't have a fork parent. But when you're forking from user space, you always have a fork parent. So we end up passing that range allocator to page directory. And what that does is it just replicates the state of the parent process's range allocator, so that because you end up running with the same address space, right? And you have the same allocations in the forked child. So if you unmap something in a forked process, because the range allocators have the same state, at least at first, then it's able to deallocate it and everything works as you would expect. So let's look at how page directory is constructed. Create for user space. Page directory. Where can we see the constructor, please? Okay, so when we create a page directory, we initialize the range allocator like I was just talking about, either with a parent range allocator, in which case we make a clone of that state, otherwise we make a new one. And here we pass in the virtual memory range that it's supposed to like hand out, and we have that hard-coded up here. This is the user space range base starts here, and the kernel space range base starts here. And page directory, here, first thing we do is we call populate page directory, and what that does is that it just puts in all of those kernel mappings into the user space page directory, so that every user space, every process's page directory has just a copy of the kernel page directory, and then that's how we have everything mapped into every process. Like the kernel is mapped into every process, although it cannot access the kernel memory because it has a privilege level that it requires. So you would get a segmentation fault if you try to access the kernel memory, but it is mapped. You just have to call into the kernel, and then the kernel has everything already there, basically. So what this does is just copies all of the kernel page tables into the user space page table. And then we also set up a mapping from our page directory map so that this is used in some places where we want to go from a CR3 value, a page directory register value, to a page directory object. So this is just a way for us to be able to look that up. And then here, this is for this helper right here. You can look up a page directory by the page directory. What the heck does the B stand for? I don't even remember. Page directory base, right? I should probably change that name. So this is how we are able to figure out, just based on CPU register state, we can figure out which page directory object is currently in effect. And when we're looking up a region with only a virtual address as the input, that's useful for that. Anyway, so that's how a page directory is set up. Now, if you look at what members it has a pointer back to its process. So page directory is either owned by a process or it's the kernel page directory. And they all have a range allocator. And then they have a directory page. This is the one page that, so page directories are 3-level. So the first level is the page directory, and then they all point to page tables. Or is it 2-level? Whatever. It's multi-level. So you have the CR3 points to your page directory, and each page directory entry points to a page table, and then each page table entry points to a page. Yeah. So I don't know if you would call it 2 or 3-level, but this is the directory page. So the root page in this particular page directory is here. And then we also keep a hash map of all of the physical pages that we have gotten from by allocating them out of a physical range. This is just so that we know, or no, what's this for? This is for keeping them alive, right? Because when you deallocate a physical page, then it will be returned to the physical region allocator. So this allows us to keep them alive here. Whenever we allocate a physical page for a process, we add it to this physical page's hash map with its index. I think actually this is only the physical pages for the page tables itself. It's not all the physical pages that the process is using, just to be clear. So this is just for the metadata of the page directory. Right. So now in process, we have created a page directory which has a range allocator. Maybe we should look at range allocator as well. Range allocator, as I mentioned earlier, it manages a virtual address range and is able to allocate and deallocate virtual addresses. So there's no memory being allocated here, only addresses. It's an address space manager, basically. And it has, this is the meaningful API, really. Either you're allocating anywhere, then you just give it how much memory you want, and it gives you an address where you have that much memory available. Or you can allocate specific, where you say, I want this specific address with this specific size, and this may fail, of course. Both of them can fail. You might have no more address space, or in this case, that it might be busy, like there might be something already allocated there. In that case, this will fail. And then you can deallocate a range, which will put it back into this available ranges vector here. And this thing is actually sorted and merged and stuff automatically. So that's what that is. Now, so if we look at how processes are started, though, they actually get started in do_exec. This is where we load a binary and map all of the ELF segments and stuff so that you can run the program. Now, the way we do that is here, first we just open the executable file and see that everything is right, and then we create we stash away the old page directory of a process, because now we're in exec when you want to execute a binary in a program, right? So we store away the old page directory in case we need to restore it, and then we create a new one like a fresh address space. And in this fresh address space, we create an inode VM object referring to the executable file. And first thing that we do is then we make a region where we allocate a new region with this VM object as its backing store. So if we look here, so the very first thing that happens when we execute a process is basically that we create a inode VM object, and this is the executable, so like something like bin sh. Oh, that looks weird. Inode bin. Why is it doing that? Frickin' OpenOffice or LibreOffice or whatever. So just imagine that. Oh, okay, there we go. So we create one of these that refers to this, and then that's this object right here. And then we also allocate a region that, this means that allocate anywhere, basically. We don't specify an address, and we just say how big the file is, and we want to use this VM object as the backing store for the region. And this is the offset into the VM object. So in this case, we want offset 0 because we want to do the whole file, right? So that's this, and then this is the name of the region, and this is the permissions. So in our case, we only want to be able to read from it. And then we assert that it worked out because we're expecting it to work out every time. And then we create an L floater, and we do the L floating business. And how this works is that the L floater has these callback hooks. So whenever the L floater finds a program section that it wants to map, then it calls this hook, and we allocate a region with a specific virtual address. So this is provided by the L floater, but we're always using the same VM object. So when we're loading a program, it's actually kind of interesting that we just create one inode VM object, and then all of the different program sections are all regions that point to the same inode VM object. So I can show you what that looks like if we bring up System Monitor, actually. If you look at some, we have a shell process right here. So we open a memory map, and we can see, oh, wait, what am I doing? So here is this is exactly the region that I was just showing you, that contains the whole program, and it's read-only. We could probably make it not even readable. And then here are two sections mapped by the L floater, and this first one is read and execute, and it's mapped at this virtual address. And then the second one is the data segment, so it's read-write, and it's mapped at this virtual address. And these actually come from the elf headers. So if you were to read elf-l on the shell binary, then we can see that this 8048 is this segment right here, and this is the 88A is this guy right here. Of course, they don't end up exactly at the same location because we have to align it to a page, but they are these two. So that's how that works. And then I realized now that maybe we should load this thing correctly. We're probably not doing that, but something to fix. But yeah, so that's those. And what do we want to talk about next? I guess we can talk about what happens when you have an inode VM object. How does it actually load from the file, right? So because we just create one here that refers to an inode, but then when you access the memory, because lfloater here, he will just we just pass him the virtual address of that region as a pointer, and then elf loader will go and create an elf image, but essentially they will just read from that pointer. We're passing in the pointer, and we call parse. Can we finally read from it? Yes, here. So header, we're reading the raw data that we passed to the elf loader. And the reason that this works is because the first time that you do that, if you're trying to read a piece of memory from an item object that we haven't loaded from disk, you will get a CPU page fault. And that's a special exception that you get in the CPU that says, hey, you're accessing memory, and the page table says that this thing is not present yet. So what happens then? I'll show you where we enter. So we have a interrupt handler set up for interrupt 14, which is handled by the page fault assembly entry. So this is just a piece of assembly code that that executes whenever a page fault happens. It's this thing right here, but it's just setup code that will call a C++ function. This one, page fault handler. And when we get a page fault, then we have some interesting state that we can look at. So we have the CR2 register contains the address of the access that failed, and CR3 contains the address of the page directory that failed, or not failed but faulted. And then we try to figure out, is this a fault in user space or kernel space, blah blah blah. But then the important part is right here. We call memory manager handle page fault. And then depending on what this function returns, we will either, we may crash, for instance, if this thing says responses that we should crash, but it can also say continue. And hopefully we'll get continue, so the page fault was benign, and this thing here can take care of whatever happened. But if we do crash, then we run this code here, which, potentially sends the seg fault signal, and then tries to do some heuristics to figure out what kind of crash was this, why are we crashing, and then eventually crash the process by calling handle crash. But let's look at handle page fault. So handle page fault, it gets this page fault object, which is just containing the error code and the address. And the error code tells us whether this was a read or a write. And is this a not present error or a protection violation error, some stuff like that. So first thing we do is we check, is this a not present error for an address that's in kernel space? If so, this can happen where the kernel allocates a bunch of memory, and then we create a process. The process gets his own copy of the kernel page tables, and then after that, the kernel goes and allocates some more memory. And then we have processes with outdated kernel page tables. So what happens then is that they will get a not present error. And so we catch the page fault here, and then we just copy over the current mappings from the kernel page table to the user space page tables. So this is a semi-common thing that happens. Otherwise, what we try to do is we want the region object to handle the page fault. So we got to figure out, for this address that's failing, it's a virtual address. So it's an address not in physical memory, but in virtual memory. So we have a virtual address, so we want to find the region that manages this particular address. So that's what we do here. We call region from virtual address. And what this does is, we looked at this just earlier, but basically it looks either in the kernel region set or in the user space region set to figure out which page directory, or to figure out which region is this page fault in. And then we come out of here. Either if we don't find a region, that means that this is some invalid address. It doesn't have a corresponding region, which is what happens if you just try to access some address that you don't have allocated. So then you will get an error fault here, and we will return should crash as the response to this page fault, and then we saw that what would happen, that we would just crash. But if we did find a region, then we ask the region to handle the fault. So we go here, and then now we get to sort of figure out what kind of fault is this really. And that really depends on some more of the region metadata that we have now. So first thing we look at is this page not present? And if so, is this page not readable? Because if it's not present and the region says that the region itself is not readable, which is what happens if you protect a region with prot none, for instance, then it becomes not readable. So if you try to read from it, you'll get this fault. And we look at the region, see it's not readable, so we'll crash you. But we were interested in the inode thing. So what happens next is page is not present, and the VM object of this region is an inode. This means that it's an inode VM object, basically. And if we get here, which is where we are now, we call handle inode fault. And when we handle an inode fault, then what we do is, first thing, we want to take the paging lock of the VM object, because multiple processes can use the same inode VM object, right? So we got to take a lock here. I don't like this code, but this is what it looks like right now. So we'll block here until we can get the lock. This means that we are the only people modifying this VM object at the moment. And then we check if there's already a physical page in the VM object for this particular access. So each of these faults, they get an index into the region, and if you look here, the index is the index of the physical page. So when you get a page fault, the page fault tells you like this particular page in this region is missing, say. And the page fault, the purpose of the page fault now, the handler, is to provide that page or crash. So this is the index in the region of the page. So in this case, the index in the region is probably 0, right? But the index in the VM object is 1. So that's what we do here is we create a reference to the VM object's physical page entry, to this guy right here. And it's the first page index of the region plus the page index in the region. So this would be 0, this would be 1, right? So now this thing here, VM object physical page entry, it's this thing. And then after we acquire the lock, we have to check if it's non-null, because if somebody had the lock and they took care of this specific fault, so we just erased here, then somebody may have already populated this slot, and if so, we just return, basically. We say like, okay, fine, I will map this page that you provided into my page table as well, and then just continue. But if that didn't happen, which is the common case, then here we just log a little counter of the number of inode faults, and then we enable interrupts, and we call to the inode. So we had each inode VM object refers to an inode, right? So we have the inode here in the VM object .inode, and then we ask the inode to read some bytes, and this calls into the file system code, which will read the bytes from disk or wherever they come from. And you don't know how long this will take. It might take some time. That's why we have to enable interrupts, so you can get preempted during this. And then after we read all of that memory from the file, then we disable interrupts again, and then now this is the part where or I should mention, we read the file into a stack buffer here that we have. So we don't allocate anything yet, but it's only once we've actually made sure that the read was successful, so we don't crash because of a failed read. Now we allocate a physical page. So now we actually allocate a user space physical page, which comes from the no, it's not here, but it comes from the physical region thingy. I guess we can see how that looks like. So we call find free user physical page. which just walks all of the physical regions and tries to take a page from one. And if we get one, then we return it. And we can optionally specify whether we want it to, or we specify whether we want it to be zero filled or not. And if we want zero fill, then before returning the page, it uses this quick map mechanism that I mentioned earlier. So it quick maps the page, just fills it with zeros, and unquick maps it. And in our case, we say that it shouldn't zero fill because we've already read a page from a file. And if it was a short read from the file, so it didn't fill up the whole page, then we memset the remaining bytes here. So we don't need a zero filled page because we're about to copy a full page into it anyway. So we just avoid the zero fill here. And if we are unable to allocate a physical page, then we crash the process at this point. So that's sad, but it's what happens. And but if we were able to load it, then we map the page. And mapping here just means that we actually put the allocated page into the process page table, which makes it now accessible at that pointer address. And that's what we do next is we just create a pointer to the newly allocated page. And this pointer is like the real deal. It's like the real pointer in the process address space, the way it's ending up. And then we just memcopy this stack allocated page buffer, which contains the 4 kilobytes from the inode that we read from the file system. We memcopy that to the destination, which is the newly allocated page, and then we return should continue. So this bubbles up to the wait, what was I changing here? Let's not save whatever I did. What was it? Region handle page fault. Handle fault, right? So we called VM object handle inode fault. So here we'll return continue, hopefully, and then this guy here, memory manager handle page fault, returns continue. And then here in the exception handler, we don't take this path, but rather we take this path, where we just continue after a resolved page fault. So that's how pages are dynamically loaded from disk when in an inode VM object. I hope that made sense. So next, maybe we can look at anonymous VM objects. So these are created, for instance, when you call mmap. So mmap does a lot of checking first, and then what you can get is either you can get a purgable VM object if you pass the map purgable flag, or you can get a regular anonymous VM object. And in those cases, let's look at those first. Then we just go to allocate region. First thing allocate region does is allocate a range. So this is a virtual address range. So now we are here. The process is doing a mmap call, and we ask the range allocator, hey, can you give me some memory with this size? And this can be an empty address. In that case, it will give us memory at any address. And if it's, if it's 0, then it will give you anywhere. But if you specify an address, then we'll try to give you that address. But if that doesn't work out, we return null putter, and mmap will fail with enomem. But assuming that it worked, we add the region to the process's mRegions vector, which is here. This is the thing that keeps region objects alive, by the way. So they are owned by this vector. And we have the next thing we do is we append it to this, and then this is just a way of saying the last appended thing. So this is refers to the region that we just added. We map it into the process's page directory. And process always has a page directory, so this returns reference, right? So when you allocate a region, is created and then immediately mapped, which means that it immediately becomes part of the process address space. And then we have this optional flag called commit, and if commit is true, then we call commit on the region. And what commit does is that it immediately allocates all of the physical pages. So when you allocate a region, if you say commit, then you get, if you allocate 1 megabyte, then you get 1 megabyte of physical pages right away. If you don't say commit, this is what your VM object looks like in the new region that you just allocated. It has no physical pages. And that's the default mode. So you allocate a gigabyte of memory, you get a region, it's 1 gigabyte large, but it doesn't have any physical pages. We will populate those physical page slots because of page faults that happen. So whenever you try to access a piece of memory, if we start out like this, right? Then you access the first page, then now it would look like this. So that's what happens with those. Now, the way that that works is that when we get a page fault for one of these regions, where do we create the VM object actually? So we call create user accessible, which creates a new region object. Region. Right, so we call this constructor where we instantiate a new anonymous VM object with specific size. And this here is this constructor, which is this constructor, and it just creates a VM object, and we create this array. It's a fixed array of physical page pointers, but notice that they are ref footer, not non-null ref footer. This means that they all start out as null. So you start out with no pages. That's what you get. And then the way that we populate those pages is when you first access each page, you'll get a page fault. And we'll go to the handle fault in region. And now we get the page is not present, it is readable, but it's not an inode, then it has to be a 0 fault. And then we go to handle 0 fault. So what a 0 fault is that it's a page that we've allocated for you, but we haven't actually put a page there yet. We only have the address allocation, not the physical memory allocation. So we call them 0 faults because the thing that we're going to do is we're going to allocate a page and then we're going to fill it with zeros. So first thing that we do here is make sure we take the paging lock so that no one else is modifying the same VM object that we are, since they can be shared between processes. And then we do the same thing as the inode fault, that we check if while we didn't have the lock, did somebody else finish the allocation for us? If so, we just map what they allocated and continue. Otherwise, we log the event for the statistics. And then here we call allocate physical page, and now we say 0 filled, because this time we want it to be 0 filled. And of course it can fail, in which case we'll just crash, because not much else we can do here at the moment. Obviously, we want to make allocate physical page fail as little as possible, so we're going to try to put more smarts into that. But here, basically, this thing is going to be smarter, and if he still fails, we have no choice but to crash this process, right? Because we can't continue if we need a page and we can't get a page. Nothing we can do. So we crash. But if we did get a page, we just add it to the list of physical pages here in the VM objects. So we put it in the physical page entry, which I guess refers to one of these guys. And then we call remap page, which updates the address mappings in the page table so that this address, the virtual address, now points to the specific physical address of the page that we allocated. And maybe we can look at the physical page object actually. Physical page. It's a very, very simple object. It just contains a physical address, and then it has a reference count, and then some bits here that say if it can be returned to the page free list or not, and if it's a supervisor page or not. But the important thing to know about it is that it is reference counted, although I notice here that it says retain count, which is the old name for reference. But anyway, it has this special behavior that if it may return to free list when it is when it reaches the 0 references, then it will be returned to the free list, which is the memory manager's physical region thing. So that it goes back in that bitmap where we were keeping the physical pages. Anyways, so that's what the physical page class is. It's just a physical address and some metadata bits. So that's the 0 fault. And of course, if you look in System Monitor, maybe I should have used this to illustrate a bit more. We just look at System Monitor itself, for instance. When you look in memory map here, what you're seeing here are regions. These are all, each row here is one region. So this is the virtual address base of the region. This is the size of the region in bytes, and this is how many bytes are actually backed by a physical page. That's how many bytes are resident. So you can see here, for instance, that we have 4 megabytes of stack virtual address space allocated, but only 12 kilobytes resident, which means that we only have 3 physical pages because we didn't get any page fault beyond 12 kilobytes into the stack yet. But if we do get a page fault because you put some big object on the stack or something, it will allocate another page, zero it out, and then return control to the program transparently without him knowing that there was no stack there originally. And you can see some of the access bits here too. R is for read, W for write, T means that it's a stack, and then we have S for shared. So we know that this mapping here is a font that's mapped by many processes, so it's a shared mapping. And this one here is a purgable memory, so it's we didn't talk about those yet. I guess we will soon. But yeah, and I wanted to show you the faults. So we can see the number of faults that have happened in each process too. Like these are the number of inode faults. So in the system monitor, we can see that we have had 196 inode faults so far. It's not that many, but it means that we had to read 4 kilobytes from a file 196 times in this process. 0 faults ticking up steadily here. That's the fault that we were just talking about, where we have some piece of memory where we've allocated a VM object, but it's not until we get that first page fault where we have to actually allocate a page and zero it out, provide it to the user. And then the next type of fault, I guess, is cow faults, which we can talk about too. So cow faults are copy on write, and it's something that happens when you fork a process. Then we create this thing called a copy on write mapping, because forking is initially very cheap. Because what forking does is creates a clone of a process, right? So a forked child is basically identical to its parent. The only thing that's differing is the PID and the return value from the fork function. Other than that, they are identical as far as they can tell. So how that works is that we don't actually make a copy of all of the memory in that process, because that would be very costly. Like you fork and now you have twice the memory consumption, right? So what we do instead when you fork is that we make this thing called a copy on write mapping, which is where we, when you fork, then we go through all of the regions in the process and we clone them. So in the child process, we append a clone of the parent region. And what this does is that it creates a new region object that uses the same, has the same address, uses the same VM object and everything. And for shared memory, we don't have to do so much, because shared memory is just 2 regions that point to the same VM object and that's it. But if something is private memory, so not shared, then we do this thing called a cow region. And actually both in the parent and the child, that region becomes cow, and it means that we have this cow bitmap where basically every page in that region now, whenever you write to it, that means that you're modifying what should be your unique private copy, your unique private memory, but it's actually shared until the moment that you write to it. Because up until that point, they're identical, and we know that. But if you write to it, they diverge. So we protect the region to make sure that we get told if you try to write to it. So we put a write, we disallow writing to this region, so that causes a page fault. And the way that happens is, wait, how am I doing that? Right, ensure cow map. So every region has a cow map, and it's a bit for every page in the region that says if this page is written to, should we make a private copy of it or not? And the first time that you write to one of those pages, we clone the page and we set the cow map bit to false or 0. So we only cow each page once. I hope this is making sense. I've never had to explain cow before. But if you look at how the page fault is implemented, then we can see handle fault. So it was not a 0 fault. So we get down here instead. So if it's a write, attempt to write is the reason that we're faulting, and the type is protection violation. So we're trying to write, and the region is writable, but we should cow this particular index. So this, because if it would not be writable, that means that you're writing something that you're not supposed to write to. But if you are supposed to write to this, but we still got a fault, something is weird. So we look at this bit. Should we cow this page? Aha, that's why we are getting a protection violation for our attempt to write. So we call handle cow fault. And here, I haven't looked at this code in so long. So the first thing we do is we look at the physical page in the VM object, and we check if the reference count of the physical page is 1. That means that although we are supposed to cow this, there's only one reference to it, which means that we are the only ones using it anymore. So there's no wait, does this make sense, I wonder? Does this actually make sense? Because now I'm wondering, I think the idea here is that if nobody else is using this, so it's marked as shared, but it's not actually shared, then the reference count of the physical page would be 1. But I think the reference count is always going to be 1. Or is it? Because the regions don't add. The regions don't add to the reference count. Okay, I'm not sure why this works. Oh, I'm getting concerned. I'm guessing that we never actually take this code path. And let's say if and def. I just want to see if this code runs. Yeah, remap, rewrite. Okay, this runs. Why does this work? So the idea, at least, do we ever not take that code path then? The idea is that we should continue only if it's a shared page and somebody is using it. Okay, let's see if somebody is ever using these. Somebody is using it. Okay, so there's something here I'm not getting. But I don't want to get too deep into debugging right now. But why would the VM object page physical page slot have multiple ref? Why does because the reference count of each one of these guys should really only come from the VM object pointing to it, which is what makes it so strange. So I'm just confused when it would be more than one. But okay, anyways, we'll just talk about the spirit of this code, and then I'll have to go back and investigate this closer. But so the spirit here is that if the ref count is 1, that means that only this VM object, or only this region, refers to this physical page, so it's not shared with anyone. There's no need to cow, so we clear the cow bit, and we remap the page. So in this case, we don't have to make any clone or duplicate of the page. But if we are sharing the page with someone, and we want to write to it, then we have to make our own copy of it before we write. So here we steal the page from the VM object. Oh, wait, is that how it works? Region. Where do we clone the region? Clone the region. Oh, shit. Okay, so this is why it works. When we clone the region, then we clone the VM object. I didn't realize. So, and when you clone a VM object, what we do is that we copy all the physical page pointers. So we have a second VM object, which, let's see, it would be something like this. Second VM object, there are no regions into it yet, and it has the exact same physical page pointers. So now the reference count of these guys is 2 instead of 1. But it's not the same VM object. So that's how it works. Interesting. Oh, I'm glad I figured that out. Otherwise this would be a annoying cliffhanger. So this does work. So what we do here is we take the page that we're going to copy, we move it out of the VM object, and then the VM object now has an empty slot here temporarily. Of course, interrupts are disabled, so no one can mess with us. And then what we do is we allocate a new physical page, and if that doesn't work, we crash, of course. Then we quick map the new page, and we mem copy the old page to the new page, and then put the new page into the slot, unquick map the new page, which we could probably do here as well, but it doesn't matter because interrupts are disabled anyway. And then we turn off the cow bit so that we don't get told again that this thing needs to be copy and righted. And then finally we remap the page, which updates the page tables so that you can now continue running. And effectively what happens here is that you have a piece of memory that you inherited from your fork parent, you write to it, and the kernel actually interrupts the process at that point and gives you a fresh copy, a unique fresh copy of that page you were trying to write to, so that you're not writing into the same address space or same memory that the parent still has. So the parent remains exactly as it was when you forked, and your clone becomes unique instead of being shared. And this just handles that transparently. I feel like I either explained this too much or too little. I'm not sure, but let me know what you think. Anyway, so if we look at the number of faults of this kind, we can see that it's not the most common fault. It happens a little bit whenever you fork and you do something in the child, then you write to some memory, you end up overwriting something. Almost everyone does, but not everyone, it seems. Anyways, but it's important to note that when we clone a region for cow, then can we get to it? Then the parent region that we're cloning from also becomes cow. So whether you write to the memory in the child or the parent of a fork, in both cases you have to cow so that your page becomes unique. And I guess that's where that optimization comes from that I couldn't understand at first. And we'll cow fault. Because say that you're sharing something with a child, and then the child goes and cows the page, then he will remove one reference here, right? So in the parent, the ref count is now 1. So if you write to that memory in the parent after the child has already cowed it, there's no need to cow again in the parent. We actually just remove the cow bit and remap the page. So there's no copy made in that case. That's why that works. Wow, it's kind of clever. I feel like I wrote this code. I think I did. But anyway, there are probably smarter tricks that you can do with this stuff. I just haven't discovered them yet or learned about them yet. If you know some cool cow tricks, let me know. So I guess next we could talk about purgable memory. Although I made a bunch of videos about it recently, but purgable memory is a concept where you have a piece of memory, and actually maybe we should look at VMObject just to show you the different subclasses that exist. So these are the 3 subclasses: anonymous VMObject, purgable VMObject, and inode VMObject. And we've talked about anonymous VMObject, which is what you get from mmap. We talked about inode VMObjects, although did we ever look at what that actually contains? So this is an inode VMObject. It mostly just has a pointer to an inode, and then some notifications and gunk that happen. And anonymous VMObject, it's very, very simple. It has no special members, just some helpers and stuff. But purgable VMObject has a little bit of state. So he has a volatile flag, which is what makes purgable memory special. And then it also has a was purged flag. And what this is about is purgable memory is memory that you can allocate, and the kernel can take it from you if the kernel decides that, well, I need that memory more than you do. And we see here the volatile flag. These particular memory allocations, these regions here are purgable VMObject backed, and this is their volatility flag, the volatile flag. You can see here these two guys switching back and forth. This is actually the backing store of the window. So let's look at someone that's not updating quite so much. So the taskbar here, we have a volatile region, and what volatile means is that if the kernel runs low on memory, it is okay for the kernel to take the physical pages that are inside of this region and just use them for whatever it wants. And the process is in the taskbar in this case is not going to freak out if that happens. And that's because of the API around purgable memory that makes sure that you'll know that the kernel did this. It's just you put yourself in a state where you don't crash and you don't fall apart just because that happened. And it's all with this volatile flag. So when the volatile flag is set, so the memory is volatile, it means that the kernel can take it. But if you set it to be non-volatile, it means that the kernel promises, I won't touch this memory until you set it to volatile again. And when you're setting it to volatile, using the madvice API, so you call madv set volatile, it will, when you set it to non-volatile, then we will return whether or not the memory was purged while it was volatile. So basically, it's volatile for some time. You say, hey, now it's going to be non-volatile because I want to use this memory. And you can't take it from me now because I'm using it. When that happens, we also return whether or not it was purged in the meantime. So this is your cue to know if it was purged, I can't trust the contents of this memory anymore. But if it was not purged, whatever I left there, it's still there, and I can use it again. This is extremely useful for building up big caches of things that you can stand to live without them, but if they stick around, that's great. And for instance, decoded images that are not essential for your screen contents right now, but might be useful later. Or I think another common example is like if you're doing a music player, you can batch up decoded songs, but you can be like 2 songs ahead or something, or 3 songs ahead, but only the song that you're playing right now really needs to be in memory. The next upcoming 2, you can decode them as a nice to have, but if the kernel decides it needs that memory more than your upcoming songs needs it, then it can take it away. And then when it comes time to use those in your music player, and then you would set them to non-volatile, you would learn, hey, I actually took that memory. And then that's when you know that, okay, fine, I'll decode them again then, geez. And Purgable, excuse me, Purgable VM object has this API called purge. This is what the kernel calls if it wants to throw away all of the pages in that VM object and steal them for himself. Jeez. And what happens there is that we take the paging lock, so no one else can mess with this VM object, and then we just iterate the entire physical pages vector or array of the VM object and just clear them all out. And this will cause the destructor of those pages, those physical page objects, to run and put them back in the free list. And of course, we have to remap every region that uses this VM object afterwards, because now those pages are not there anymore, and we need to get some 0 faults if you try to access them. And that's what this will do. Or you'll get a not present fault, and then you'll determine that to be a 0 fault because the page is missing. And right now, we don't actually have any smart integration in the page allocation with the purge thingy. We just have a call to purge. You can make a syscall purge, and that will just walk the entire VM object graph and purge everything. So this is something to work on in the future. Of course, we want to integrate this with the page allocator. We want to have some proactive stuff happening, but we're not there yet. But it could be worked on. And I'm pretty excited about purgeable memory in general. I spent half a day explaining it to people on Reddit. I hope everyone finally understood what it's good for. And I guess is there something more I would like to talk about? Should we look at something else? I guess we can look briefly at private versus shared VM objects. So if you map some anonymous memory and you say that it's shared, then we have this shared bit in the region, and the thing that we do with that is, I think it's only ever used when we clone a region. Wait, where the heck are we using this? mshared, right. When we're cloning a region, so you fork, then we clone all the regions in the parent, right? And if a region is shared, which means that it was not mapped with map private, if it's shared, then we use the same VM object as the underlying VM object for the region in the child process. That's if it's shared, or if it's not readable. If it's readable but not writable, then we also do that. I'm not sure that this is super correct. Because I don't like that one. Shared but readable, not writable, because you could change that. Shared readable. share read-only things between parent child. What if child that makes no sense. What if the child protects and overwrites things? Shouldn't they just be cow mapped instead cowed? I think they should just be cowed, but that's something to work on. Anyways, so that's how the shared bit works. If the shared bit is set, then we fork will use the same VM object. But if a shared bit is not set, we'll just imagine that this code is not here. Then we fall down here and we create a cow region. So I think basically that's everything that I have to talk about today. I hope I covered interesting things, and I hope you learned something. And I definitely encourage everyone who's interested in this type of stuff to go and check the code. And anything that you have questions about, you can always ask. I'm happy to talk about any of it. And I'm sure that there are many improvements that can be made, and I'm happy to learn about those too. But yeah, this has been a little code tour run through of the virtual memory system. So thank you for watching and for hanging out. And I already said I hope you saw something interesting, but I really do. And I will see you next time.